Hello and welcome to Lecture 4 for the course ECE 254B Parallel Processing. Now with this lecture, we enter part 2 in the textbook, which has been split into two parts because of new material that has been added. Part 2 prime deals with shared memory parallelism, and part 2 double prime deals with the circuit model of parallel computation. Each of these was originally two chapters, chapters 5 and 6 for shared memory, chapters 7 and 8 for the circuit model. Now part 2 prime consists of the original chapter 5, and chapter 6 has been expanded into 6a, 6b, and 6c. I've done this in order to keep the chapter numbering in the rest of the book so that when you use the textbook, you're not confused with the different chapter numbers. So today I will cover chapter 5. In lecture 5, I will cover chapter 6a. And these are basically shared memory algorithms. And in lecture 6, I will cover chapter 6b and 6c. I will combine them into a single lecture. Okay, so this is basically a restatement of the chapters. Shared memory is the most intuitive parallel user interface, as we will see in today's lecture, that once you sort of define your parallel computation model, it's pretty natural to write algorithms. And we can use our experience in sequential programming. A lot of it transfers here with some changes. So it's pretty easy to develop algorithms. On the other hand, the shared memory model that we will use today and in the next lecture ignores implementation issues. So it's convenient as a programming model, but because it ignores implementation and hardware issues, it may not be the most efficient. So the argument is made, this is sort of like using high-level languages to program a sequential computer. We know that if you directly write programs in machine language, you can make them more efficient. On the other hand, the convenience of high-level languages is something that is very important, and we are willing to put up with some inefficiency in order to achieve that convenience. Also, it's possible to develop compilers that take this high-level notation or model and convert it into a hardware level program. And of course, the smarter the compiler, the more efficient the actual hardware level program becomes. Okay. So today we will describe the PRAM, Parallel Random Access Machine model. This is basically the parallel extension of the RAM model, RAM. It's unfortunate that this acronym also has been used for random access memory. But random access machine is basically the von Neumann model that we have been using all along. A computer that consists of a processor, a memory with locations, addresses, and we can access those locations randomly. That's random access machine. The parallel version of that is called PRAM, or parallel random access machine. So why are we starting with shared memory? Basically, the reason shared memory and circuit model were combined into this part is that these are the two extremes, the two extreme models of parallel processing. Shared memory is very abstract. It ignores implementation details. As I mentioned, it's sort of like using high-level languages to program. The circuit model, on the other hand, is the most concrete. In other words, we will be dealing with actual circuits that if we want, we can go into the lab and actually implement them and run the algorithms that we develop on them. So it's very close to the hardware. It's very realistic. When we estimate delay and cost, it's very close to the actual reality of how much delay signals will experience and how much the circuits will cost. The circuit model allows explicit latency area energy trade-offs, whereas when we deal with shared memory, we don't have much control over how much energy is used, how much area is implied in the hardware implementation, and so on. Because we are removed from the hardware. Now, once we have studied these two extremes, 3 lectures each, we'll study other models that fall between these two extremes. In other words, they're not as abstract as shared memory, and they are not as concrete, as close to hardware as the circuit model. So that's the plan for the rest of the course. So what is PRAM? PRAM is a parallel machine consisting of P processors, you see them on the left here, and M memory locations, shown on the right of the diagram. Each processor can access any one of the M memory locations at will. So you see those lines basically say that processor 0 can access location 0, it can access location 1. So all of these M locations are equally accessible to any one of the processors. Now the machine is envisaged as follows, works as follows. It has cycles, so it's a synchronous machine. Within each cycle, there are 3 phases. So 3 things are done in each cycle. The processor within a cycle begins by fetching a value from some address Si. So processor I fetches from some address Si, and these addresses can be different for different processors. So each processor has an address from which it fetches, and the memory is assumed to support this kind of multiple access to multiple locations. The processor then performs computations on the data held in local registers. So the value that was fetched goes in some register, and there are other values in registers, and some computation is performed by the processor. And then finally, the processor stores a value into address DI. Again, DI is a number, an address that is associated with processor I. Okay, so all 3 of these phases are performed in every cycle. A memory access takes place, some computation on register contents occur, then value is stored in memory. And this is repeated as long as we have a program to execute. Now, because multiple processors are trying to access multiple memory locations, it is possible, given that these numbers Si, for example, S0 and S1, we have no control over. The processor decides which location to fetch from, which location to store in, and they could be the same location for 2 processors, okay? So because of this, we define 4 submodels of the PRAM, parallel random access machine, depending on whether reads from the same location are allowed by multiple processors, If they are not, we call it exclusive read. If they are, we call it concurrent read. Similarly, for writes to the same location, we can have exclusive write. In other words, only one processor can write to any specific location. And concurrent write, multiple processors can write into the same location. So there are four basically submodels of PRAM. EREW, exclusive read, exclusive write. This is the least powerful and most realistic model. We'll see in what sense later. Concurrent read, exclusive write. Concurrent reads are allowed, but writes have to be exclusive. This is usually the default model. If we don't specify the model, this is usually the one that is assumed. Concurrent read, concurrent write. Both concurrent reads and concurrent writes are allowed. This is the most powerful model. And then we'll see that it's further subdivided. And finally, ERCW, exclusive read, concurrent write. And this is not useful because if you allow concurrent write, concurrency in writing is more critical because reading, multiple processors reading from the same location semantically does not create any problems because they all get the same value. Whereas concurrent write, where multiple processors write into the same location, we have to sort of worry about what happens. Okay, what actually happens in memory when this takes place. So because we are allowing concurrent write, but not concurrent reads, this is sort of illogical. So it's not used. The other three: exclusive read, exclusive write, concurrent read, exclusive write, and concurrent read, concurrent write. So here are examples of program segments in pseudocode that use exclusive read, exclusive write, and so on. Exclusive read is exemplified by this program fragment. For I between 0 and less than p, so basically all processors numbered 0 to p minus 1, processor I reads from location I. So processor 0 reads from location 0, processor 1 reads from location 1, 2 from location 2. So they're all reading from different locations, therefore this is an example of exclusive read. Here's an example of exclusive write. All processors, for all processors, processor I writes into location I plus 1 modulo P. Again, these are all different locations. Processor 0 will write into location 1. Processor 1 will write into location 2. Processor 2 will write into location 3. And then this is modulo P. In other words, we wrap around. When we get to processor P minus 1, processor P minus 1 writes into location P modulo P, which is location 0. Again, all the locations the processors are writing into are different. Concurrent read is exemplified by this program fragment. Again, processor I, all processors do this. Processor I reads from location I modulo 2. Now, I modulo 2 can have two values, 0 or 1. So this basically means even-numbered processors will read from location 0. Odd-numbered processors will read from location 1. So there will be P over 2 processors that will be reading from each of these two locations. Therefore, this is concurrent read. And finally, example of concurrent write. The ith processor writes into some location di, where di is an arbitrary number. So because they're arbitrary number, it's entirely possible that two or more processors will try to write into the same location. Okay. I mentioned that when you do concurrent write, you have to define what happens. What does it mean? when two processors, for example, write into the same location. And these are various submodels, various ways of defining concurrent write. The first one is CRCWU, where U stands for undefined. The value written is undefined. So we do allow multiple processors to try to write into the same location. However, the hardware or the system provides no guarantees as to what will be written. Some arbitrary value, undefined value, will be written. In other words, the hardware does not prevent this from happening. It does not explode or anything. It's just that you don't know what will be written there, some arbitrary value. Detecting concurrent writes, CRCWD submodel, a special code for detected collision is written. So if two processors write into, say, location 0, one tries to write, let's say, number 5, one tries to write number 10, then what is actually written into that location is a special code. So that if you later go and read from that location, retrieve the value, that value tells you that multiple processors tried to write into this location. It won't tell you what they tried to write. You just get an indication that they tried to write into this location. This is a useful capability to have. It's better than the undefined case, because at least you get a sense that you get information about multiple processors trying to write into that location. A common CRCWC, and multiple processors are allowed to write into the same location as long as they try to write the same value. So processors 0 and 1, if they both try to write the number 5 into location 10, then the number 5 actually will be written into that location. Okay, random, the value that is written is randomly chosen from those offered by the multiple processors, CRCWR. So if multiple processors try to write the value 5, 10, 20, 25, one of these 4 values will be randomly chosen by hardware. We have no control over it, and written into that location. A priority model, CRCWP, the processor with the lowest index succeeds. So the processors have an implied priority. Processor 0 has the highest priority, 1 has the next highest priority, and so on. Multiple processors try to write into one location, the one with the highest priority, the one with the smallest index, lowest index, will succeed. And max and min submodels, these are actually 2. The largest or smallest of the values is written. So in the example we're talking about, if 5, 10, 20, 30 are written, then the value in the minimum submodel 5 will be written. In the maximum submodel 30 will be written. And finally, the most powerful submodel is reduction. And different kinds of reductions are possible corresponding to the S submodel, the A submodel, and the X. So the arithmetic sum of the values, so if these are numerical values being written, maybe the sum of them will be written. This actually means that the memory is endowed with processing logic so that the multiple numbers coming in are added and then written into memory. It's not a very practical model, but theoretically, we can entertain this model and develop algorithms for it. Logical AND, so if the processors try to write bits into a location, the logical AND or logical XOR of those values, or any can define other submodels. Some other combination of these values will be written. Now, a subset of those submodels you see here, EREW, CREW, CRCWD, detecting, CRCWC, common, CRCWR, random, and CRCWP. And they are ordered by their power. In other words, EREW is the weakest, least powerful of these models, the ones written here, and CRCWP is the most powerful. What do we mean by less or more powerful? A model U is more powerful than model V if the running time for a problem of size n under model U is upper bounded. If the rate of growth of this running time is upper bounded by the running time for V. Furthermore, this is not big O, it's little o, which means this is strictly less. So this may be logarithmic time, okay? This may be linear time, meaning that this is strictly faster in terms of asymptotic complexity than this one. So this is the sense in which, in other words, there are algorithms and we can run strictly faster on CRCWD compared with CREW, and there exist algorithms that run faster on CREW compared with EREW. Now, even though this hierarchy exists among models from the least powerful to most powerful, the difference is not that great. In other words, this theorem 5.1 states that P processor, CRCWP, priority PRAM, the most powerful of these, can be simulated or emulated by a P processor EREW PRAM, the least powerful, with a slowdown factor theta log P. Okay? In other words, the difference between these two is at most a factor log P in complexity. So this basically motivates us to use whatever model is most convenient for our algorithm program development, because the difference is not that great. Remember that we are aiming to write parallel algorithms that have polylogarithmic running time. So we'll be satisfied, for example, if the running time of the algorithm is log squared of p, or log squared of n, if we have n data items. Now this factor log p slowdown will make that log cube p instead of log squared p. It is still polylogarithmic, and therefore we really don't care that much, don't mind that much that the factor log p slowdown. So if this model allows us to develop algorithms more efficiently, more conveniently, faster, then we use that. Of course, if we develop the algorithm for the EREW, then that requires less powerful hardware to be executed. The difference is no more than log P. Okay, so this is basically the outline of a proof why that's the case. The multiple steps, basically we start with, I'm assuming here 9 processors, numbers 0 to 8. Each of them try to read. Let's say we are talking about multiple reads, concurrent reads. Okay, write it will be similar. So they're trying to read from the locations of their choice, and these locations are their repetitions. So location 1 is being read by processor 0, by processor 6, and by processor 7. So we have concurrent reads here. Okay? So in order to eliminate the concurrent read, in other words, emulate this algorithm on model that does not have concurrent reads, is exclusive read, we do the following. We sort this list by the address that is being accessed. Okay, so these three, in these three, location 1 is being addressed, so they come first in the sorted list. Location 2, location 3, 5, and 6. So we need a sorting algorithm to sort these according to this address. Once we have done that, we compare each of these values with the previous one, and this can be done in constant time because each processor, say processor 1, compares this to the previous one, processor 2 compares this to the previous one, and they're using exclusive read because processor 2 reads these two locations, processor 1 reads these two locations. So if we do it in 2 steps, we don't need concurrent read. And then we eliminate all the repetitions, redundant. So this access is removed, this access is removed. Only one access to location 1 is kept as a representative of all the accesses to location 1. Only one access to location 2, one access to location 3, and so on. So the sorting itself will take logarithmic time. Okay, well, we'll see how later. For now, let's accept it. That sorting takes logarithmic time. Removal of these redundancies takes constant time. Now we can go ahead and do the accesses which are exclusive. Processor 0 access location 1, processor 3 access location 2, 4 access location 3. So we do this access again in constant time. Then the rest of the process is basically to provide this value to those other 2 processors that also needed it. This will be done by basically copying this value into these 2 locations, copying this value into this location, and copying this value into this location. And this can be done by a parallel prefix computation. Again, we'll see later how, in logarithmic time. So logarithmic time sorting, constant time removal of repeated elements, constant time access to memory, and then logarithmic time, basically replication of these values so that we have 3 copies of this value that was read, and therefore the 3 processors that need it can access that value from different locations. So we succeeded in assuming that we can do sorting in logarithmic time and parallel prefix computation in logarithmic time. We succeeded in emulating the most powerful model in this series on the least powerful model, the log p slowdown. Okay, so the bottom line is that we need not be too concerned with the CRCW submodel used. Simply use whichever submodel is most natural or convenient to you as you develop algorithms, and basically rest assured that that model can definitely be emulated by EREW with no more than logarithmic factor slowdown. Okay, so let's now start developing algorithms for PRAM. We have several algorithms. Simple ones we'll discuss in this lecture, and some more complicated ones in the next lecture. So suppose we have an n vector, a vector of length n in shared memory, and we want to initialize all elements of this vector to zeros. Okay, this is a typical thing that happens when you do vector computations. You may want to initialize a vector to all zeros before you compute values and put them in the vector. So the vector has n elements, and we have p processors. So the p processors basically can initialize p elements of the vector to 0 in constant time. Processor 0 will write into this location, processor 1 into this, processor 2 into this, and this will be exclusive write, so no problem. So in every cycle of PRAM, we can initialize P elements, and then the next P element, because there are N over P segments, we need N over P steps. And the last segment, of course, may be smaller than the other ones if N is not divisible by P. So this is the pseudocode. For J equal to 0 to N over P minus 1, so N over P 0 is this 0th segment, N over P minus 1 is this last segment. Processor I does this. So processor 0 is in charge of putting a 0 here, putting a 0 here, putting a 0 here. So more generally, processor I will put a 0 in the ith element here, in the ith element in the second segment, in the ith element in the third segment. And that location will be JP plus I. So if J equal to 0, the first execution of this loop, processor I will write 0 into location I. The next execution, J will be equal to 1. It will be P plus I. P plus I will be basically the ith element in this next segment. Okay, then we say if h is less than n, in other words, if we have not overshot the end of the vector, and the memory location, B is the base address of this vector. Memory location B plus h, where h is this JP plus I, is set to 0. Okay, very similar algorithms about the same level of complexity can be written for adding 2 n vectors and storing the result in the third. Let's say that we have 2 vectors, n vectors with base addresses B prime and B double prime. We want to add those two and store the sum of their elements into vector B. And I'll leave it up to you to write pseudocode similar to this for that. Slightly more difficult is convolution of 2 n vectors, where we have 2 vectors, and then we compute a result vector, where the kth element of the result vector is ui times vj, where I plus j, the indices sum to k. So for example, if this index is 5, we will have u0 v5, u1 v4, u2 v2, and so on. All those elements must be multiplied and the result added to form the kth element of this vector w. Okay, the second algorithm, a simple algorithm, is broadcasting. Broadcasting is basically when one processor knows or has a value and wants to inform all other processors of that value. Of course, if we have concurrent read, that's very simple. The processor that wants to broadcast writes into a particular location, and then every other processor will go and read from that location. If you allow concurrent read, then they can all read, so it takes a constant time, single step. The broadcasting processor writes, all processors read from this. Okay, what if we don't have concurrent read? How do you broadcast? The idea is that this single value that one processor writes into this location will be copied into, so if we have 12 processors numbered 0 to 11, we have a vector in shared memory that also has 12 elements. This single value is copied into all the other elements, and then each processor will go and read from its own private location. So processor 0 will read from location 0, processor 1 will read from location 1, and so on. And because that value was copied into every location, they will all get the same value and the broadcast has been achieved. So the algorithm for doing this uh, is an instance of what we call recursive doubling, a recursive doubling scheme. So here it is. Each processor takes the value in one location and copies it into the next location. So processor 0 reads this location and copies it here. Processor 1 reads this location and copies it here. Processor 2 reads that location. And of course, all of these processors 1 through P-1 are doing useless, redundant work, but it makes the algorithm simpler. So we say processor I read from location I and copy the value into location I plus 1. Okay? At this point, we have two copies of that value that need to be broadcast. Okay? This original value and the copy that was made by processor 0. Then we instruct each processor to read from processor I, read from location I, and copy it into location I plus 2. Processor 1, read from location 1 and copy it into 3. After this step, again, there are a whole bunch of redundant copies here that are not useful. We have 4 copies of the data to be broadcast. The next step, we do processor I, read from I, and copy into I plus 4. Now we have 8 copies, and then the final step is done. So this is the pseudocode. For k equals 0 to log 2p minus 1, basically this is the number of iterations, log 2p iterations. Processor J between 0 and p, basically all processors do the following. Copy bj into bj plus 2 to the k. So when k is equal to 0, this will be bj plus 1. When k is equal to 1, the next iteration, this will be bj plus 2, then bj plus 4, and so on. Okay, now this algorithm has a bunch of problems. First of all, it has all these redundant copying. Now, redundant copying may or may not add to the running time of the algorithm, because if actually all processors can access memory locations at the same time in the same amount of time that one processor accesses a location, then this doesn't imply additional time. However, still it creates unnecessary memory traffic. Memory accesses take place that are really not needed. And because memory tends to be a bottleneck in parallel processors, remember the concept of memory wall that we discussed earlier, it's best if we avoid these redundant copyings. Also problematic is that processor 11 in the step 0 will try to read this value and copy into location 12, which is not part of this vector. So it basically may corrupt data that is outside. Similarly here, this one may try to copy further down and so on. So it's pretty easy to modify this algorithm to avoid both redundant copying and also copying outside the boundaries of this array. And if we do that, this will be basically what happens. A single copying occurs here, 2 copying, 4 copyings, and in this case also 4 copyings because we avoid going beyond the end of the array. Okay, I leave it up to you to discover how to modify the algorithm to do that. Okay, this is a class participation for when we have in-person classes. So I'm going to skip this. If you're interested, you can read it. It's basically the next algorithm that I'm going to describe is emulated by students pretending to be processors. Each student is given a number. and then we try to sort the list of numbers by following the algorithm, and students pretending to be processors that follow the commands of the program or algorithm. So this is basically the algorithm. It's called all-to-all broadcasting. So we talked about broadcasting before, when one processor wants to notify all the other processors about a single value. Now suppose each processor has a value, and we want each processor to notify all other processors of its value, so that at the end, every processor knows the values of every other processor. Okay? So the idea is that we have a vector in shared memory that has p locations. You can imagine that processors will write their values here. Processor 0 will write its value, processor 1, processor J, and so on. Now we have to allow all the other processors to go read all of these values. However, if we write the algorithm such that we say, okay, first go read location 0 to all processors. Then go read location 1, we need concurrent read. We need a concurrent read model. We are trying to write this by exclusive read model. Now the solution is pretty simple. Basically, processor 0 begins reading all these values from location 0. Processor 1 begins reading these values from location 1, and then when it gets to the end, it wraps around and goes to location 0. Processor 2 will start from location 2, goes all the way to the end, and then wraps around and reads 0 and 1, location 0 and 1. So at any given time, different processors are accessing different locations because they're sort of out of phase with each other. So this is the pseudocode. First, that's the initialization phase. Processor J write own data value into BJ. So all the values to be broadcast are now in this vector. For k equal 1 to p minus 1, so there are p phases because p values have to be read by each processor. Processor J does this. Read the data value in B sub j plus k mod p. Okay, so processor J starts with j plus 1 in the first iteration, and it reads j plus 2 in the second iteration, j plus 3, and because it's mod p, it will wrap around and read the remaining values if there are any. Okay, so assuming that we have this all-to-all broadcast algorithm, here is a very naive, by the way, that algorithm is time optimal because each processor needs to be informed of p-values, and when it accesses memory, it can access just one value. So you need p steps, no matter what algorithm you use, and this algorithm does it in p steps. Okay, now this naive PRAM sorting algorithm uses that all-to-all broadcasting algorithm. So each processor has a value, and these are the values that we want to sort. It writes 0 into RJ. RJ is the rank of the value in processor J. So we initialize that rank to 0. And every time we detect a value that is smaller than the value that processor J holds, we increase that rank by 1. So for example, if the number held by this processor is 5, and we see that some other processor has 3, that means the rank of 5 is at least 1, because there's at least one value that is smaller than it. Then later, if we see a value 2, the rank will be incremented by 1 again, becomes 2. Okay, so for k equal to p minus 1, processor J, the following. uh, compute this L, J plus K mod P, if SL is less than Sj. So it's basically comparing its own value Sj to other values, in turn going through the list. And if that other value is smaller than the processor's own value, then the rank will be incremented by 1. Also, it's possible to have repeated values. So the value SL may be equal to Sj. Now in sorting, doesn't matter in what order these equal values come, we decide that if L is less than J, in other words, if this equal value occurs in earlier in the list, then we increase the rank. If it doesn't, if it comes after, then we don't increase the rank. And finally, once the ranks have been determined, processor J writes its value Sj into the element in S corresponding to its rank. So if its rank is 0, it writes into S0. If its rank is 1, it writes into S1, and so on. So the list will be sorted. So this takes order P steps, because basically the bulk of time is in this all-to-all broadcasting. Basically, every processor sort of tries to learn about the value of all the other processors. And as we saw up there, this takes P steps. Of course, this is not a very efficient algorithm. Remember that sorting on a sequential computer requires order P log P time if you have P elements. Okay, so here we have order P, so the speed up is only order log P. Okay, we'll see later that much faster sorting algorithms are available, but they're also more complicated. Okay, the next algorithm is the semi-group computation, where we have a list of elements, let's say numbers, and we want to add all of them together. Again, the recursive doubling method can be applied. So this notation that you see here, so there is a value in location 0 that processor 0 provided, location 1, location 2. This 0 to 0 means this is the sum of values going from 0 to 0. So basically one value. So a single value is stored here, a single value here, and so on. Then we use the algorithm structure is very similar, almost identical to the recursive doubling that we use for broadcasting. Basically, processor 0 goes and takes this value and adds it to this. Processor 1 takes this value and adds it to this. So now we have this value was added to this. So this is 0 through 1. Two values are included here. 1 through 2. Two values are included here because this value was added to this one. Okay? Then we do a two-step away addition. So this value will be added to this. So the value 0 we added to the sum of 1 and 2. We get 0, 1, and 2. When I say 0, 1, and 2, I don't mean the numbers 0, 1, and 2. The 0th value, the first value, and the second value. And then 4, and then 8. And then we have that sum of all the values from the 0th one to the 9th one here. Then we can use a broadcasting step to inform all the processors of the semi-group computation result. This is something I leave up to you to read. In fact, it's a subject of one of the problems at the end of the chapter. Okay, what about parallel prefix? Well, it turns out that as we tried to do the semi-group computation, we obtained parallel prefix results right here. So parallel prefix, ironically, is simpler than semigroup because that last broadcasting step is not required. So this is the first value, the zeroth value, the sum of zeroth and 1, the sum of 0 first and second, the sum of 0 first, second, and third. So all the parallel prefix values are already available there. Okay, so this is again an instance of recursive doubling. You see that initially just one value is correct in the set of values that we are trying to compute, and two values are correct, then four values are correct, then 8 values, and eventually all 10 of them. This could have been 16 because the next doubling will go from 8 to 16, but we had only 10, so we still need 4 steps. Okay, this is another algorithm. It's called the divide and conquer, an instance of divide and conquer algorithm for parallel prefix computation. We'll revisit this when we talk about the circuit model. This is more suitable for a circuit implementation. So basically what we do, we take pairs of input elements. So we have x0 through xn minus 1. Okay, x0 and x1 are combined, give us this value. x2 and x3 are combined. So if this is addition, they are added, and so on. And a half-size parallel prefix computation is performed because we have half as many values here as we started with. Then half of the outputs are already the correct values. So this one, for example, is x0 plus x1. And in parallel prefix, the first input basically just goes to the output. So this is x0 plus x1. And this is x2 plus x3. So the first output of this prefix computation is the sum of these two, x0 plus x1 plus x2 plus x3. So this is 0 through 3. So half of the outputs that we are seeking are already available. The other half, for example, the sum of values from 0 to second is the sum of value from 0 to 1 to the first plus x2. And this one, the sum of values from 0 to 3 plus x4 gives you this. Okay, so this as a circuit, if you look at it, the latency of the circuit from input to output is the latency of this half-size. So if you basically use the same method to design this half-size circuit, so this is a recurrence, the latency with p inputs is the latency with p over 2 inputs, this yellow box, plus 2, where 2 is 1 unit of time at the top. So I assume this operation, whatever it is, addition, multiplication, takes 1 unit of time. 1 unit of time there, and 1 unit of time down here. The solution to this recurrence is 2 log 2p. So this is a logarithmic time circuit for performing parallel prefix computation. We can also program this on PRAM if you want. You basically compute these. You recursively call the routine that does parallel prefix computation, and then you do these operations at the end. So even though this is primarily developed for circuit implementation, you can program it on PRAM. This is another example, another way of using divide and conquer. I won't go through this because we'll come back. The advantage here we do parallel prefix on even index inputs and a separate parallel prefix on odd index inputs. So there are two half-size circuits. And then a bunch of elements down here. It's easy to verify that these are the desired output. The problem with this one is that it assumes commutativity. because it combines 0, x0 and x2 first into here. Okay, before, so the order of operations is not taken into account. x0, x2, x4 are operated on by this circuit, x1, x3. So what you have here, if you take this output of the top circuit, that's x0 plus x2, and this output of the bottom circuit is x1. So in the case of addition, it doesn't matter. You'll be adding x1 to x0 plus x2. But if the operation is not associative, this doesn't give you the correct result. So this is only valid for commutative. Sorry, I may have said associative for commutative operations. Okay, however, assuming that the operation is commutative, the advantage of this circuit is that the latency is only log p instead of 2 log p, because these two half prefix computations are done in parallel. Therefore, the time for only one of them is considered, and only one extra unit of time for these boxes at the bottom, circles at the bottom. So this is a faster circuit, but it requires the operation to be commutative. Okay, here is a very interesting parallel algorithm ranking the elements of a linked list. I have to define this because you may not have seen this problem. So we have a linked list. You probably know this from your data structures or algorithms course, where each list element has some information stored in it and a link that points to the next list element. So this is a head pointer, points to the beginning of the list. And then at the end, this element points to itself, signaling that this is the end of the list. Now we want to determine the distance of each element from the end of the list. We call this the rank of the element. So this is the end element, so the distance to the end is 0. The distance of this one to the end is 1. This one is 2. So these are called the ranks of the various nodes of this data structure. We are interested in computing these ranks, okay? Now the problem seems at first glance to be hopelessly sequential. In other words, we can't get any access to this element of the list without traversing these links. Okay, there's no random access to elements of the list. We have to sequentially traverse the list until we get to our desired element. So you may wonder, how can this be speeded up? Of course, you can do it in order p very easily. If there are p elements, then basically what you do, you count the elements, and you notice that there are 5 of them, and therefore the rank of this one is 5. The rank of, so there's a rank vector. Okay, so this is the first element of the list. So initially you write rank equal to 1, although this is not the final rank. And for this one, you write 2, and so on. And then once you know what the number of elements is 6 minus this rank that you wrote. So 6 minus 1 will be 5. 6 minus 2 will be 4. So there's a simple algorithm to do it. But we want to do things in parallel. And it's not immediately obvious how we can use multiple processors to sort of tackle parts of this problem without having to go through all those links, okay? So here's the data structure that we assume in shared memory. Each of these nodes, let's say, is a word in shared memory. It has an information field and a next or link field. So the head points here. The information part is C, and the link part is 5. So it basically points to here, which is the next element in the list, information part F, link part 0, then A, and so on. So these two vectors in shared memory define this linked structure. There is a third vector in shared memory where we will compile the ranks. At the end, these elements, so this one will contain the rank of this element. So the rank of the node with information part A should be 3. So at the end you get 3 here. The one with B should be 1. You get 1 and so on. Okay? So how do you do this? How do you overcome this sequential nature of the data structure? Here's the idea. First, initialize all the ranks to 1, except for the last one, which we initialize to 0. And you know which element is the last one. So imagine that processor 0 is handling this node, processor 1 is handling this node. So each processor will look at the link and see if it points to itself, in which case it initializes the rank to 0, otherwise it initializes the rank to 1. I'll show you the pseudocode in a minute. So here is the key idea. These ones basically means the rank of this element is 1 more than the rank of this element. The rank of this element, so the rank of each element is 1 more than the rank of its successor. Okay? Now, if I go here and say, okay, the successor of this node is this one, and the successor of that one is this one. So I change this link to point directly to that one and add 1 to 1. This is 1 more than that one. This is 1 more than that one. So 1 plus 1 is 2. The rank of this one is 2 more than that one. Of course, I'm destroying the data structure. So if I don't want to destroy the original data structure, I just make a copy of it in constant time. Each processor copies basically one of those nodes. And then I proceed with this algorithm. In the next step, this one points to this one, and this points to this one. So 2 plus 2 is 4, and I change this link to put directly the successor of the successor. So this is the successor, this is the successor of the successor, and therefore, and then one more step, I'm done. Now all these nodes are pointing to the terminal node, the last node, and each one has its correct rank. And it needs a logarithmic number of steps because, again, the span of these links doubles in each step. The span is 1, it's 2, it's 4, and then eventually 5, which is the maximum it can be. Okay, so this is the pseudocode. It's a little bit more complicated than the previous ones, but not much more. Each processor initializes the partial ranks. If next of j equal to j, if this equality holds, then that's the terminal, the last node. Then rank of j equal to 0, else rank of j equal to 1. So that's the initialization phase where these values are stored in the rank vector. Okay? So that's the initial. While rank of next of head is not equal to 0. See, we know we are done with this process when the rank of the next of, so the head points to here, next of head will be this one. When this one is pointing to the last node, then we are done. Notice that in the next to the last step, this is not pointing to the last node, it's pointing here. So the rank of next of head is not equal to 0. But once we get to this point, we stop. While rank of next of head is not equal to 0, each processor do this. Rank of j is equal to rank of j, the current rank of j, plus rank of next of j, rank of the element that this one is pointing to. And then next of j, the pointer of this node, becomes the pointer in the next of j. Okay? Let me make sure we understand this. So the pointer, this is the node j, this is next of j, this is next of j. So that pointer in the next step points to next of j. And we are done. So a question for you to consider, I won't answer it here, is which PRAM submodel is implicit in this algorithm? Answer is CREW, but I want you to think about how you can modify this algorithm in order to use EREW. The reason it is CREW is that when you access the next element of this one and the next element of this one, so the processor that accesses the next of this one is accessing this node, and the processor that accesses the next of this one is also accessing that node. So they're basically going to the same location in memory. This is a pretty easy process to remove that requirement, that concurrent read capability, and implement the algorithm with exclusive read. Okay, the last problem for this chapter is matrix multiplication. This is a familiar problem, so it should be pretty easy to understand. In matrix multiplication, we're talking about square matrices here for simplicity. Matrix A is multiplied by matrix B. The result matrix is C. Element ij of matrix C is obtained by multiplying row I of A by column J of B. And this is what this says. Element ij of C is aik bkj. So ai1 bj1, b1 b1j, and so on. So basically, if these are m by m matrices, m multiplications take place. These are the m multiplications, and m addition. So you initialize the running total to 0. So the two loops for I and j, basically we are focusing now on computing this element inside this double loop. Initialize t to 0. T is the eventual value of this. For k0 to m minus 1, do this. T equals t is set to t plus aik bkj. And then when you are done with this loop, cij is set to that t value, and you are done. So a sequential algorithm for this is order m cube, because 1, 2, 3 loops with m iterations, that's m cube. And the operation performed in the innermost loop is 1 multiplication and 1 addition, and therefore is order m arithmetic, order m cube arithmetic operations. Okay, so the first one of these that uses m cube processor, I'm going to skip. It's not interesting. So let's start with using m squared processors. This is still unrealistic because for parallel processing, we are interested in huge matrices. You know, we do parallel processing when you have huge matrices. Otherwise, you don't need parallel processing. So if you have, say, a 10,000 by 10,000 matrix, 10 to the 4 by 10 to the 4, you need 10 to the 8 processors in this algorithm, which is impractical. Let's go through it because it helps with the understanding of the rest of the steps. So if you have m squared processors, you assign each processor to compute one element of C. And the processors, instead of being numbered 0, 1, 2, 3, and so on, they're numbered by pairs of indices. So processor ij will be responsible for computing element of j of c, and that processor initializes the value to 0, and then it basically reads elements of this row one at a time and elements of this column, performs this multiplication and this addition. So this now requires order m steps. You have only one loop, okay? So we went from order m cubed steps for sequential algorithm to order m steps using m squared processors, which is pretty good because with m squared processors, you can have a speed up factor of m squared, order m squared, and this is what we are achieving here. So the algorithm runs m squared times faster than the sequential algorithm. Okay, remember that this now requires concurrent read model. It's exclusive write because each processor will be writing into a different location of C. We don't write into A, we don't write into B, and into C, processor ij writes into this location, and other processors will be writing in other locations. So it's exclusive write. But it's concurrent read because this processor reads row I of A, but the processor here, ij minus 1, also will be reading row I of A and column j minus 1 IB. So all the processors in this row, computing the values in this row, will be reading this. Okay? However, because the order of multiplications is not important, we don't have to go from k0 to m minus 1 for all of them. So this one maybe can start reading A from element j and then go to the end and come back. And similarly, column B from element j, go to the end and come back. And exactly the same things will be multiplied by each other, and the ordering is not important. And now the processor next to this, which is column j minus 1, will start reading this from j minus 1. Therefore, they will never try to access the same location at once. So we can use EREW with this trick. Okay, now if we have m processors, then we can assign each processor to compute a row of the result matrix. So it will compute these elements in turn. As it tries to compute these elements, it will be reading row I of matrix A. So row I is read only by this processor, the processor in charge of computing this row. But it will be reading different columns of B, depending on which of these elements it's computing. And therefore, again, the same trick can be used to ensure that here we don't need concurrent read. So here we now have m processors, and we have m squared running time, order m squared, because we have two loops. The processor one loop is basically stepping through these elements, and the other loop is stepping through the computations needed to form this ij element. Okay, so order m squared time with m processors, again, optimal speed. Okay, m may still be large. As I mentioned in the example of 10,000 by 10,000 matrix, we may not have 10,000 processors, as many processors as rows. So this is what we do. We assign a processor to compute multiple rows of the result matrix. Okay, I won't go into the details. So if you have p processors but more than p rows, each processor will be responsible for m over p rows, and the same thing now applies, the same kind of algorithm. Processor will have one loop to go through these rows, compute one loop to go through elements of that row, and one loop to compute a single element there. So again, we require order m cubed divided by p steps using p processors. Again, we have optimal speed. Now, one problem this algorithm and all the previous one is that they require too many memory accesses. Let's look at this one. Okay, when you access this AIK from memory BKJ, you perform one multiplication and one addition. So therefore, for each pair of memory accesses, you do two arithmetic operations. So the number of memory accesses is roughly equal to the number of arithmetic operations. Now, arithmetic operations are pretty fast. Memory accesses are pretty slow. So this is really inefficient because the processors will do a lot of waiting while values are fetched from memory. Now, a solution to this is to use block matrix multiplication, and this is actually the way practically matrices are multiplied. So here's the concept. If I have a square matrix, let's say even dimensions, I divide it into four blocks, four submatrices, A, B, C, D, and also this one into four submatrices, E, F, G, H. I can multiply these two matrices as if these were 2 by 2 matrices, except that the product will be matrix multiplication and the sum will be matrix addition. So matrix A, submatrix A times E plus B times G will be this part of the result matrix. Okay, so I'm multiplying, let's say, 10,000 by 10,000 matrices by multiplying 5,000 by 5,000 matrices, smaller matrices, and then getting the result that I need. Okay, so this gives me an idea, and this can be extended to more blocks. So for example, you can divide this into 4 by 4, 16 blocks. The same principle applies. So if you divide this into 16 blocks, 4 by 4, it's as if you're multiplying 4 by 4 matrices and you're forming these submatrices of the result. Okay, so if you have P processors, let's say we have 16 processors only. You divide your matrices into 4 by 4 blocks, and you assign one processor to compute one of these blocks in the result matrix. So here, if you have 4 processors, then you divide your matrices into 4 blocks. Then you assign one processor to compute this, one processor to compute this. So these are the 4 processors, okay? So the processor that computes this will have to read elements of this matrix A, elements of matrix E, multiply them, elements of B and G. So that's basically a smaller matrix multiplication problem. And then add the result, add these two matrices to get this. Okay, so here I've shown the block ij of the result being computed. So this is not one element of the result matrix, but a block. So these are blocks. And these blocks are q by q, where q is m divided by square root of p. Square root of p is basically how many blocks you divide each dimension by. And then m divided by square root of p is, we call it q, which is the size of these small matrices that we operate on. So when you multiply these small matrices, basically, I won't go into the details of this diagram. The multiply-add computation on Q by Q blocks of matrices needs 2Q squared memory accesses. Okay, remember I said, so this is my Q. Q squared accesses to read A, Q squared accesses to read E. So if I want to multiply A by E, I need 2Q squared memory accesses. But it requires 2Q cube arithmetic operations. Therefore, the ratio of arithmetic operations to memory accesses will be Q. If this Q is fairly large, so if these blocks of matrices are, let's say, 50 by 50, then for every 50 arithmetic operation, I will have one memory access. So this is a significant advantage. I'm reducing the number of memory accesses as I execute this algorithm. Okay, so this block matrix multiplication is the algorithm of choice in practice. Okay, let me stop at this point, and lecture 5 will deal with chapter 6a, which is a lot of material from the original chapter 6 plus some additions. Bye for now. Take care and stay safe.